Good morning, afternoon, and evening, everyone. Here I'm showing you a beautiful map of the sky as observed from Earth. You can see many stars, these little points of light, the bright and dark lanes of our Milky Way galaxy, and even these two smaller satellite galaxies in the bottom. As I start the timer, you'll see colored circles start to pop up, and those represent detections of planets around the star in that circle. And these are called exoplanets, planets outside our solar system, so orbiting stars other than our sun. The color of the circle corresponds to the detection technique, but that's not so important right now. The size of the circle corresponds to the planet's orbital size, so how quickly it's orbiting its star and how far away it is. And the sound frequency that you will hear corresponds to the orbital frequency of the planet. So shorter period planets have higher notes. Overall, exoplanets is still a relatively young subfield in astronomy, but has grown rapidly. And now we know of over 4,000 other worlds. So how did they form? What are they made of? And are any of them like the Earth? Today, I'll share with you how Trello is helping us to address these questions. So my name is Johanna, and I'm an astronomer at the Earth and Planets Laboratory at the Carnegie Institution for Science in Washington, D.C. And I have the pleasure of working with this great team, shown here, to find and characterize planets around other stars. I'm particularly interested in understanding the compositional diversity of exoplanets. And to do this, we need to not only detect the planets, but also measure their sizes, their radii, and their masses. And we can put those together to give us a bulk density of the planet and thus a bulk composition. So how do we learn about exoplanet composition? In the next few slides, I'll walk through a couple of different observational techniques to do this. First, we use the transit technique to measure the planet radii. And for this technique to work, the planet has to pass between us and the star in our line of sight. We see small changes in the star's brightness. And if that happens periodically, and we can rule out other potential sources, we can infer if there's a planet there. We can measure its size and also its orbital period by how frequently those dips in the star's brightness occur. This is an indirect detection technique in that we're not actually measuring light from the planet, but from the star itself. And the latest instrument doing these kinds of observations is called TESS, the NASA Transiting Exoplanet Survey Satellite. And this instrument is scanning the entire sky in this orange slice pattern, starting in the southern hemisphere and then moving to the north, to find new nearby transiting exoplanets that are also amenable to making the mass measurements, so we can have the radius and the mass to get the density and then the composition. Like with the transit technique, we measure planet masses by observing changes in the star's light. But unlike the transit technique, we do this using ground-based telescopes and instruments. These planet mass measurements are called the radial velocity technique because we measure how the star's velocity changes over time. So you can see in this graphic, as the blue dot, the planet, orbits the star, the planet is clearly moving around, caught in that gravitational well of the star, but the star is also moving in a much smaller orbit due to the influence of the planet. We can measure the star's motion towards and away from us in its orbit by monitoring how features in the star's spectrum change. And that's that rainbow bar with the lines at the bottom. I don't have time to go into all the details of stellar spectroscopy, but suffice to say, when you disperse a star's light, like with a prism, you not only get a rainbow, but also imprints of the different atoms and molecules in the star's atmosphere. That's shown by these dark lines and bands in this spectrum, which is of our star, the sun. When the star moves, so do the relative positions of these lines, which we can measure with great accuracy to detect planets and measure their masses and also orbital periods. As I said, we make these measurements from the ground, in particular using this fantastic instrument built by Carnegie scientists called the Planet Finder Spectrograph, or PFS. We mount this instrument on the Magellan II telescope at Las Campanas Observatory in Chile. We collect stellar spectra over time, over the course of multiple nights. We look for changes in the star's velocities that might indicate the presence of planets. So now that you're all experts in how we make these measurements, where does Trello come in? We've been using PFS to find planets since 2010. And before TESS launched, it was a somewhat simpler time. The time on Magellan, the Magellan II telescope, is competitively awarded twice a year, in semester A and semester B. And astronomers from partner institutions are allowed to apply, and telescope allocation committees at each of those institutions evaluate and rank their proposals, and then they're all combined into a schedule for a given semester. In that time, there's light time when the moon is out, and dark time when the moon is not out. And our stars that we observe with PFS are considered fairly bright, and so we work in bright time. PFS is scheduled on the telescope in blocks of time, like you see here, usually about 2 weeks at a time. And before TESS launched, the Carnegie team, which here I'm just calling Team 1, we were getting most of that time in purple. And then there were a few other people at different institutions also getting smaller amounts of time. We always run PFS in a large queue, pooling time together across the whole semester, so that even if Team 3's assigned nights are in, say, December, they can still use time in August if they want to. The Carnegie team has a long list of potential planet host stars, so stars around which we don't know if there are planets yet or not. We're trying to find them. And this list spans the entire sky, so we always have targets to observe. Usually other teams have specific targets, which they would email us a few days before an observing run, and we would print out our long list of targets and then the short list of external team targets to have while observing. Scheduling observations in this scenario was also fairly easy. There almost was no scheduling at all. Across the span of the night, stars rise and set in the sky, and the stars that are observable at the beginning of the night are mostly not observable at the end of the night. So say Team 2 had 2 targets, and the observability of the targets across a night looked like this. So the first target was very observable at the beginning of the night, but not at the end. Say Team 3 had 3 targets, and the target observability looked like this. And then I said our team, Team 1, has a long list of targets observable across the whole night. So the schedule might look something like this. A few stars to observe at specific times when they're up in the sky, but the rest just filled in sort of on the fly. We pick stars from the Team 1 list whenever there's open time, which was most of the time. But around the time that TESS launched, there was a huge increase in interest in using PFS. And this is because TESS was doing all the finding of the planets. So we didn't have to rely on PFS to do that, just measure their masses. And like I said, if you have the radius from TESS and the mass from PFS, you can estimate the composition, which is what I'm really interested in. Also, PFS is one of the only instruments in the southern hemisphere that can make these observations. And as you saw, half of the planets that TESS is detecting are in the south. So then our collaboration grew and started looking more like this. So clearly our on-the-fly scheduling was not going to work. Too many teams, too many targets, too many scheduling constraints. Just look at this observability chart. How would you even start going about scheduling observations for all these targets? It's a little bit of a nightmare. That's where Trello comes in. In the next few slides, I'll walk you through how we use Trello to help decide which targets to observe and when. First, we have to gather all of the relevant information for scheduling observations. Now, instead of a few days before the observing run, we ask that the principal investigators, so each kind of team lead, provide us with this information 1 to 2 weeks ahead of the observing run. And with our free Trello workspace, each institution has their own Trello board, which is accessible only to them and the PFS team. We do our best to keep target information confidential, although in reality, everyone's pretty friendly and rarely do they have top secret targets. Here I'm showing you an example of a board for Carnegie. So these are some of my targets. So I'm fine sharing them. And you can see that each star has a list with several different cards on it. So let's zoom into one of these lists, one of these stars. And I can show you what information we request from the PIs for each of their targets. We provided a template list, which I'll show you in a minute, which then each of the PIs can make copies of to fill in exactly the information that we want for each of their targets. So at the top, we have the target name, very important, the semester of the observation and who the target belongs to, the PI name or names. This is also a place to upload an image of the field of view around the star. So especially if there could be confusion about which star the telescope should point at. Like in this case, we have a triple star system, and we're interested in finding and measuring the mass of the planet around the A component. So we don't want the telescope to point at B or C. Next is a card that gives the priority of this target for a given observing run. We ask everyone to rank their targets just in case we have to cut targets due to weather problems, closing the telescope, or other scheduling constraints. And so we try to do that from the lowest target priority to the highest priority. And next in the list is the basic information card, which answers where is the target on the sky? What are its coordinates? That's right here. How bright is the star? What kind of star is it? Is it kind of a cooler star or a hotter star? We ask for this information in a few different formats for various logs and lists that we keep. Working our way down, next is the observation request card, which is really the most detailed. And this is where PIs describe how we should be observing the target. So you can see the exposure time, fainter stars need more time, the desired cadence, do we want this target observed once a night, twice a night, every other night, and other observing constraints. The first question at the top is the desired precision of the measurements. And this is related to the type of planet you're trying to detect. So here we have a very good precision listed because we're trying to detect a very small planet. And less massive planets cause less of that stellar wobble, so require better precision to measure the star's velocity. Here's what a template for the observation request looks like. So you can see we have very detailed instructions for the PIs. And this is because there are just a lot of choices to be made about how the target is observed, and that will affect how well the planet mass can be measured. We ask the PIs to really optimize their time to achieve their specific science goals, but those can be different for different programs. So for example, if a PI is interested in observing more massive planets, then maybe the precision they need isn't as high, but if the stars around which those planets orbit are faint, they might still need to spend 45 minutes observing each star, and they might not want us to try to observe their stars if there are clouds, because that would result in too poor quality of data. Finally, we ask that PIs tell us what exactly they're trying to detect with their observations. And this is just helpful for contextualizing their full observation request and making sure it's realistic for their science goal for detecting these planets. After we collect all the information about targets, it's time for a reality check. Is it even feasible to observe all of these targets? There are only 60 minutes in an hour and roughly 9 to 10 hours when the sun is down each night. So do all these requests fit into that time block? We create what I call a block schedule, which is kind of like a game of Tetris. And at the top here, this is actually showing similar information as those colored curve plots I showed before. So now where a target is green, it's observable, and where it's red, it's not observable. So you can see how that changes over the course of a night. In this bottom section, I have a rough idea of exposure times for each target, and within each column, I try to make the exposure times add up to no more than 60 minutes or an hour. You can see a few places where this is not the case, like red warning. Anything in italics is a target that won't need to be observed every night. So we can kind of mix and match to fit into the allotted time. All those steps have to happen even before the observing run begins. That's much more intensive than before tests, but it's all in the name of awesome science. So we're happy to do it. Once the observing run begins, we actually make a minute-by-minute plan for each night. So we take that block schedule and sort of zoom in great detail. So here's an example of one of these nightly plans. I've just blacked out proprietary target names, so you can see my target names. You can also see how long the observation should be, and then some instrument-specific parameters. We consider all that information from the Trello cards in making this plan each night. And we try to balance it out based on how much time each PI has in that semester, how much time their telescope allocation committee awarded to them. In this nightly plan, you can also see a few places where LTS is listed, and that stands for the long-term survey, which is that list of Carnegie targets that spans the whole night and the whole sky, so we can always draw from that. In fact, you can see that we actually make two plans, one for if the atmosphere is stable and one for if it's not. So this good seeing and worse seeing. We try to rely on the good seeing plan. That's what we prefer. Okay. So we keep open communication throughout each observing run between the people at the telescope and the PIs who might be at their home institutions. We make heavy use of the comment and tagging features in Trello if we have specific but not super urgent questions for the individual PIs about their targets. So this keeps questions and notes for a given target organized and searchable all in one place, which really helps our efficiency in creating these observations. We also use Slack for quick pings and have separate private channels for each observing run that are just for the people at the telescope and the instrument specialists in case there's any problems. And we also try to give general updates. So you can see here, I was very excited last December when we had really good seeing, really good atmospheric conditions at the start of our observing run. So far, we haven't actually tried integrating Slack and Trello, but it's on our to-do list. So to finish up, I just wanted to share with you a few tips and tricks that might be useful for you in your Trello case. When we're at the telescope on the edge of the Atacama Desert in Chile, we often lose internet for a few minutes, up to a few hours actually. And this can be sort of nerve-wracking. We don't want to lose that precious telescope time, but we also don't want to print out hard copies of all that information that we've collected in Trello. So instead, we actually use the Trello desktop application. As long as the observers at the telescope have opened the Trello board for the current observing run, where we put the list of all the relevant targets, that board is actually accessible even if internet goes out. So that's been a real lifesaver for me at the telescope. We also prefer to use an archive board rather than deleting lists completely. This keeps all of our previous versions of lists available if need be, along with any questions or notes that we had appended to those lists. Sometimes a PI will stop observing a target for a little while, but then decide a year or two later that they want to revisit it or remember something about their observations. And so the archive board is still searchable, and you can always move cards from the archive board back to an active board. As you saw, we're requesting a lot of observations or a lot of information from the PIs. So template lists are really key for making sure we get everything we need in a uniform way so we can execute their observations and get them the science results that they want. And finally, we found that Trello is really intuitive for new users to engage with and has increased our efficiency and decreased our stress in conducting our observations. So in this talk, I've described how we use Trello to collect and organize information and answer questions. It just so happens that in our case, the information and questions are related to distant worlds orbiting bright spheres in the sky, spread out across the galaxy. And our office buildings look like this. So you can see the two Magellan telescopes, and again, the bright and dark lanes of the Milky Way, the two small satellite galaxies to the left. And to the right, what you see is not an alien planet, but a lunar eclipse. So this photograph was taken on a night when the Earth's shadow was blocking the sun's light that otherwise reflects off of the moon. So whenever I see this image, it makes me wonder, are there other Earth and moon-like bodies doing the same dance around other sun-like stars? How unique is the Earth and its temperate terrestrial environment that pulses with life? And ultimately, are we alone in the universe? So these are the types of questions that get me out of bed in the morning, and that Trello is really helping me answer. So thanks for listening.